Thank you for downloading this podcast from Talk Radio 702 and 567 Cape Talk. For more podcasts and more information on your number one news and talk station, please visit 702.co.za or capetalk.co.za.
The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Reedy Clubby.
So nice to have you with us, Chris. Good morning.
Morning, Reedy.
Okay, now this has gotten me excited. You're saying that South Africa has been making scientific headlines or headlines in the scientific world?
Yeah, so the country has effectively created scientific headlines all around the world with the publication of a paper that wouldn't have been possible without some fossilised raindrops from South Africa. So this is a beautiful story. In fact, fossilised raindrops are not all that rare, but what South Africa does have is some of the world's oldest rocks. And this includes an ash field from a volcano that would have erupted about 2.7 billion years ago. And where this ash would have landed on the ground and been exposed to rain falling, the rain droplets have made little holes or imprints in the ash, and then more ash has fallen on top and preserved these droplets beautifully. And there is a paper in the journal Nature this week. It's by Sanjoy Som, who's from the University of Washington in America. And he and his colleagues have used these rock samples. In fact, in the press release from the university I was looking at, they have actually got a picture of a meerkat sitting on these fossils. They took a latex impression of them so they could then take the picture back to the laboratory and get a laser to scan it. And they have been able to use this data to calculate how thick the atmosphere on Earth must have been 2.5 billion years ago or so. And this is a really important question, because when the Earth was 2.5 to 3 billion years younger than it is today, so was our Sun. And that meant that the Sun was a lot weaker, less bright than it is today, because it was younger. And in fact, it would have been about 30% less bright. So the Earth would have been receiving about 30% less heat. So why was the Earth at that time so warm, and why did we have running water if the Earth was getting so much less energy? Some people have suggested this could be because there was a huge greenhouse effect on Earth at that time, with lots of CO2, and that was keeping the planet artificially warm. So knowing what was in the atmosphere would help to answer that question. So what this group were able to do is they reasoned that in the same way that a British geologist called Charles Lyell reasoned in the 1850s, but was never able to actually follow this through, if you could find samples where rain had fallen, and we know that the speed of a raindrop falling is inversely proportional to how dense the atmosphere is. So if you have a thick atmosphere, the rain falls more slowly than if you have a thin atmosphere. And if raindrops are falling more quickly, they have more momentum, and therefore they make a bigger imprint when they hit the ground. And if you can find the signs of those imprints, you can calculate how fast the rain was falling, and therefore you can calculate how dense the atmosphere must have been. That's exactly what they've done, and they've calculated it by using modern-day samples as well. They went to Iceland and got some ash from that volcano that paralysed the world's airline industry 2 years ago, and they repeated the experiments by dropping water down a staircase with a pipette onto this ash to work out how big the splatter pattern was from that. And they found that the Earth's atmosphere would have been between 50 and 100% of what it is today, compared with today, in 2.7 billion years ago. So this rules out the idea that we had a very dense CO2-rich greenhouse effect atmosphere going on 2.7 billion years ago, and something else must have been keeping the planet artificially warm.
Very interesting indeed. Our lines are open. Do remember anything that you want to ask the question, the Naked Scientist, any science-related matter, biology, health, even IT we get into sometimes. Give us a call on 021 446 0567 011 883 0702. Chris, I have this question from an 8-year-old. She walked up to me at a shopping center last week and said, please can you ask the Naked Scientist this? What substance makes up the poison in a poisonous snake?
Okay, well, the poisonous snakes produce venom, and venom comes from venom glands, and those are specialised clusters of cells which secrete proteins. In other words, they have genes in their DNA that they turn into proteins, which are short strings of building blocks called amino acids. And each snake produces a cocktail with maybe 200 or so of these proteins, in some cases maybe more. And the combination of those proteins together is what has the toxic effect. And it can range from just pain through till, obviously, death in minutes. And the snake deploys those proteins by injecting them underneath the skin. It has to do that because proteins, if you eat them, are not poisonous because they get broken down in the same way that your Sunday lunch gets broken down by your digestive enzymes and by the acid in your stomach. So the snake has to put the poison under your skin for the proteins to work. These proteins then go into cells because they have various mechanisms of getting into your cells, and they do things like turn off the ability of cells to make energy. They do things like activate nerve cells to produce very profound nerve overload, so you get pain. They also do things like activate your coagulation cascade, causing your blood to clot in lots of places where it shouldn't, so that then the blood that's washing around in your blood vessels runs out of clotting factors, so that it can't then stop you from clotting where it should stop clotting. So they have a whole range of different ways, and as one scientist put it to me, it's a massive case of overkill. And these animals probably have these very diverse mechanisms because that way it's very hard for an individual species to evolve resistance to a venom, because it's very hard for them to evolve so many different mechanisms of resistance all at once. So the snake knows that if it bites somebody, then that person or that animal are almost certainly going to perish. They're not going to get away. So getting resistant to the venom is really difficult. And many animals use similar strategies. In fact, the most poisonous animals on Earth include the cone snail, which is an Australian species which produces very beautiful shells, and it lives on the reefs around Australia. And this animal also produces a very, very diverse toxic cocktail, as do spiders. And in fact, scientists are now using these venoms because they're so poisonous. They're able to clone the genes that the snakes and the other animals use to make the venom, and then make artificial forms of the venom by making cells in a dish make those genes get expressed, and you can then use them as things like environmentally friendly pesticides, because some of these things, especially spider venoms, for example, in Australia, they've now got systems in place where you can spray the spider venom or one component of it onto plants. And because the spiders would normally eat insects, you've got a venom, a protein, which would be toxic to insects, but if a person eats the fruit or whatever the venom is there to target, the pest, then the person wouldn't be harmed. So it's a really neat way of using nature's chemical arsenal against natural pests in a way that will be biodegradable and won't have onward threats to other people or the food chain.
All right, let's go to the lines then. Neville, you're calling us from Benoni. Good morning.
Good morning. Hi. The question I'd like to ask is, where is sea level measured? And my comment is that, on the beach, it's never the same height. And I listen on the radio, if I may.
Okay.
Yeah, hi, Neville. That's a very good point. I don't know the answer. And what I will speculate is that we're talking about average sea level. So, as you quite correctly point out, if you stand on the beach, then the tide comes in and out. And so if you measured high tide versus low tide, you see difference. And so, what is sea level? So what people will be doing is looking at either average sea level, or they'll take the right extreme, a high tide, at a certain phase of the moon, and measure it at that point, so there's always consistency, because otherwise you'd never pick up the differences. So I think that's the point. And also, you're talking about sea level where on Earth, because sea level does vary on Earth because of gravitational effects. The ice caps in Antarctica, because there's ice on land there, it's not floating, it's not displacing water, but there's a huge amount of mass on Antarctica, and this pulls a bulge of water towards Antarctica, so there's like a donut of water around Antarctica. So those local anomalies have also to be taken into account. So when scientists talk about sea level, I think they're talking about average sea level, and that's by taking multiple measurements in a consistent way across multiple parts of the Earth.
Dirk in Waterfront, hi there.
Hi there, good morning. I've got I think, interesting question. I'm not sure. Maybe a ridiculous one, I don't know. But anyhow, I was reading something the other day, and they say that your physical body consists of millions of cells. And these cells die off and regenerate and regrow again. So if you think back to any event when you were like 10 years old, and I'm now in my 40s, that the actual body I have now could not have been there when I was 10 years old. Is that true?
Hello, Dirk. Interestingly, a listener on 702 and 567 Cape Talk got in touch with us about 2 years ago and said he wanted to carbon date his grandma because they weren't really sure how old she was, and he thought that, well, the family thought she may well be over 100. Because she didn't know her date of birth, because where she grew up in a remote community, such records didn't exist then, and they felt that it would be nice to know.
Yes.
And so we looked into this for him, and we approached a lady called Kirsty Spalding, who is in Uppsala University in Sweden, and she was doing carbon dating experiments on people to work out how long certain cells live, because they were trying to answer the question themselves of how long a fat cell lasts in the body, because there was this idea that you have fat cells, and the fat cells you have when you're a baby have to last you a lifetime. They found, in fact, by carbon dating DNA from fat cells, that the average fat cell lasts for 12 years before being replaced. But that's not true of all tissue. So some cells in the body, you're quite right, and in fact we think there's about 1 trillion cells in a person. That some of those cells will be the same cells that you are born with, that you die with, and a good example of this is nerve cells. So the bulk of the brain's 100 billion, 10 to the 11 nerve cells, the bulk of those will be the cells that were made when you were developing inside your mum and continue to develop for a little while after you were born. Those cells have to last a lifetime. They're not replaced. There are some brain cells that are replaced. Other cells in the body have a very short lifespan. A red blood cell that carries oxygen around your body lasts 120 days on average, and a skin cell might last a very short time, a month or so, and if it's a part of the body where the skin takes a lot of wear and tear, it might be just a matter of days. A cell that lines your intestine might last just hours. So it varies on which bit of your body you're looking at, but there are certainly some cells that are the original you. So something you were born with, you will die with. Other cells, no, their numbers up in a very short time.
I'm very fascinated by that story, Chris. Were they able to find an answer, or at least some estimate of how old the granny was?
Well, the answer we said to them was, yes, if we were to do a brain biopsy, we could get some DNA from some nervous tissue. No, I mean, we explained that different tissues will record a different age, but the point we were making is that, yes, it is possible to carbon date your grandma, because there will be cells that contain DNA, and because the DNA in cells that are long-lived is not being replaced, it will contain atoms that you brought into your body at different times in your life, and if you go to a cell which was formed when you were forming, that must be bringing chemicals into your body which you can use for carbon dating, in other words carbon-14, into your DNA and incorporating at that point in time, so you can use that as a time clock to carbon date your gran. So yes, in theory you could do it.
Okay, let's go to Brenton in Sea Point. Good morning to you, Brenton.
Hi there, how are you?
Fine, thank you, Brenton. Your question?
Thanks for a great show. I would like to know, are we seeing effects of weather patterns and crop failures as a result of global warming? And what is the risk of future famine as a result of the change in weather phenomenon? I'll listen on the radio. Thank you.
Thank you, Brenton.
Hello, Brenton. There was a paper published, I think, a couple of years ago, and it was either in Nature or Science, one of the big international journals, and they did a very big analysis, or the author of the paper did a very big analysis, looking at the same parts of the world and looking at rainfall in those areas and crop outputs in those areas, and they considered rice and wheat and maize and, I think, rye. So they were basically looking at the food staples in each area, and they were looking at the average temperatures and rainfall. And they showed a strong trend of increasing temperature, diminishing rainfall, and a corresponding reduction in food output from those affected areas. And their conclusion was, regardless of the cause, there is definitely a changing temperature signal and a changing rainfall signal, and this is translating into a changing food output, and this feeds into this whole question of global food security. There's a big concern that with currently 7 billion people on Earth, can we feed everybody? The answer is, well, at the moment we do have enough food, but there's a distribution problem. If we go to 2050, the prediction is that we will have 9 billion mouths to feed on Earth, and we can't currently feed that lot, or at least it will be a struggle. So what are we going to do about that? And so people are worrying about this kind of thing and looking at this whole question of, if global warming plays out the way that we predict that it will, what will be the onward impact of that? And the answer is that some bits of the Earth are predicted to get a lot wetter, other areas of the Earth are predicted to get a lot drier. This will have the consequence of making populations move, both of people and of animals, and that will have the complication of there being people where there may not be abilities to grow food. There will be animals where there isn't food to feed them, or it won't be possible to rear them, and as a result there'll be a bigger and bigger problem. So the effect may magnify if this plays out the way that models predict it will.
Let's go to Francois in Rivonia. Hi there, Francois.
Good morning, Reedy. Morning, scientist. I have a question regarding precession and how it influences the seasons on the Earth at the moment. If you start off with the Earth at where we are now, and precession takes 25,000 years to complete a whole cycle, the whole wobble, if you fast forward 25,500 years, the wobble will be on the other side. Does that mean we will have summer where we have winter and winter where we have summer?
Hi, Francois. It's slightly more complicated. Let me just back up slightly. So what we're referring to here is the fact that the Earth gets its energy from the Sun, and as the Earth goes around the Sun, there are a number of factors. One of them is that the Earth isn't straight up north-south in space. It's tilted at 23.5 degrees at the moment. And what that means is that as the Earth goes around the Sun, during some parts of its orbit, then the surface of the Earth will receive more solar input for longer, and other times in the orbit the surface of the Earth receives less solar input. It's nothing to do with the Earth being closer to or further away from the Sun. That's a trivial change given the distance between the Earth and the Sun. And as a result of that energy input, then the Earth gets either more or less heat, and therefore is hotter or colder, and that's why we have seasons, summer and winter. There are slightly other difficulties, including the fact that the Earth's orbit isn't circular, so that will also make a difference. And then there's this question of precession, which is that the Earth wobbles a bit during its orbit. And by wobbling, what we mean is that the degree of inclination can itself wobble a bit, so it won't always be fixed at 23.5 degrees. Sometimes it may be slightly more, sometimes slightly less. And also, the Earth's attitude in space may change. And so there's a whole range of different things, including the degree of eccentricity changing, which are all affecting the amount of energy hitting the Earth's surface from the Sun at any moment in time. And if you map all of those effects on together, you arrive at the concept of this Milankovitch cycle put together by Milankovitch. The idea being that because the Earth goes through cycles of warming and cooling, you can show that this can be explained on the basis of these wobbles. But it's not as simple as to say that the Earth will end up with an inversion of its seasons. That isn't necessarily true.
Mm-hmm. Here's an SMS here from Tabo. It says, when a bullet kills someone, what is it that kills the person? Is it the hole in the body or the poison in the bullet?
No, what's happening when a bullet hits someone is that a bullet is a piece of material, an impactor, which has a huge amount of kinetic energy, or put another way, a massive amount of momentum. When it hits the person, the bullet is small, and therefore all of that energy is spread over a very small part of the body surface, and therefore the pressure on the body surface is really high, and it's rather like you walking on someone's rather nice wooden floor with stilettos on.
I do that every day of my life.
Oh no, you're not coming around my house. You make holes in the floor. Don't go on someone's posh yacht, for example. People get very upset if people with stilettos go on their yacht because they make holes in the deck. And this is because, even though the person doesn't weigh very much, all of their mass is being distributed over a very small area, the heel of the stiletto, and therefore the pressure is really high. So the bullet has a relatively small entry point into the body, but all of that energy is then dissipated in a way that spreads out radially from the entry point as a pressure wave. And this means that all of the tissue in the path of the bullet sees this pressure wave and gets squashed very hard, and then the bullet tears through the tissue, and this pressure wave then propagates through the tissue, and the bullet then exits. And you can see this pressure wave spreading out, because usually the exit wound from a bullet is much bigger than the entry wound. And that's why, because this pressure wave has spread out, and that's what does the damage inside, because you're actually putting enormous amounts of pressure on tissue, which tears and shears and rips tissue apart. And so although the person may only have a small hole on the way in, inside the body, especially with certain types of bullet, which are designed to mushroom or flatten as they go in, and therefore they do more damage as they go through. You end up with tissue torn and ripped to pieces. Some bullets, though, will be going so fast that they can literally go in one side and out the other and do more minimal damage. Bullets which are fatter, wider, flatten, and tend to fragment as they go in, do more damage because they tear lots of things apart. So there's a range of reasons why bullets are bad. One is this pressure wave which rips things to pieces, and two, literally bullets ripping through tissue can make big holes in things like arteries, and then you bleed out. So that's a secondary effect.
Brian in Centurion.
Good morning to you, sir, and Reedy.
Yes.
Question is, a watermelon, how would you see if it's ripe? A lot of people squeeze it, thump it, squash it, you name it.
How do you test the ripeness of a watermelon, Chris? Buy sliced watermelon.
I was going to say, what I do is I slice it open and I eat it. I don't know, actually, Brian. The farmers will have a way of knowing when their melons are ripe, whether that's giving them a subtle squeeze or not, I don't know. Someone who farms watermelons, please ring me up and tell me, or tweet @NakedScientist, and I'll get onto it. Thank you, but I don't know, Brian, I'm sorry.
Sorry, Brian, sorry. Now, here's a question, Chris, that I think you will never, ever be able to answer, even if you try. Reedy, please ask the Naked Scientist, why are men so stubborn? There has to be a science behind it. That's an SMS.
I think it's probably true. It's this whole business of, do we stop and ask directions, isn't it?
Yeah.
Does your husband ask directions, Reedy?
Yes, he does. He's sweet.
Oh, okay. But yeah, okay. So maybe he's not stubborn then. But, yeah, a lot of men don't, do they? I don't know. I think it's all to do with not losing face myself. I mean, it's embarrassing. You have to stop and shut and say to someone, "Oh, I'm lost." Then it gives away the fact that you're a hopeless hunter and an absolutely useless bushman. So I think it's a sign of weakness, isn't it? That you think, I don't want to give away the fact that I'm lost, or ask for help, or admit that I'm wrong. And I think that's probably it. We're just programmed to be a bit tough-minded like that.
I should have been a man.
Do you ask for directions then? No, clearly not.
No. I just always drive on hope that I'll get there.
And is your sat-nav a lady's voice or a man's voice? Because there has been research done to find which is the best voicing to use in things like sat-navs and also in aeroplanes and military installations. Do people pay attention better to a male voice or a female voice? And the US military published on this, and they showed that in fact men and women pay more attention to another woman's voice more than a man will pay attention to another man's voice. I think it's because the blokes don't like being told what to do by another bloke, and so they go, I'm not paying attention to that. And I think they'll go for what the women say.
Oh, that was loads of fun. Thank you very much, Chris. Chat to you next week.
All right, you take care. Bye-bye.
And that's The Naked Scientist. It's always available as a podcast. The podcast is always complete. When we post it onto the website, rest assured it is complete. If you only have 2 minutes or 5 minutes, you must have done something wrong. Just try again and try to download again. It's always there.